It's in progress. Okay. All right. Hi, everybody. All right. So we're going to talk more about quicksort today. And specifically, we're going to try and build on what we talked about last time. The quicksort has this great best case and average case, but a bad worst case. We're going to talk about ways to mitigate that worst case possibility. Okay. So as a reminder, our process, the type of sorting we did before was based on partitioning. So you pick an item as its pivot. And then after you finish the partitioning process, all the items to the left are less than or equal to the pivot. And all the items to the right are greater than or equal to the pivot. Okay, that was the idea last time. All right. Now, what we observed last Wednesday, that is that if the pivot lands somewhere good, then quicksort will be theta n log n. But there's these rare theta n squared cases, which can happen in practice. For example, we have an array that's already in sorted order or almost sorted order. Or if you have an array with all duplicates, it turns out that the algorithm we described last time would be n squared. So what can we do to avoid this worst case behavior? And recall that our version of quicksort has these two properties. The leftmost item is always the pivot. And the second is that our partitioning algorithm, it always preserved the relative order of the red items and the blue items. So if we had 3, 1, 2, 4, the way we did it is we created a new array, copied over the red items, copied the white one, copied over the blue items, basically. So think about that for, 30 seconds or so. How do you avoid the worst case? And again, the worst case is, imagine the array was 1, 2, 3, 4, 5, 6, 7, 8. 1, that's the pivot. The partitioning operation takes n time, then 2 is the pivot, then 3, and so forth. So we want to avoid that problem. Okay. So I'll take a couple thoughts out loud, and then I'll tell you the usual strategies out there. Anybody have an idea? Yeah.
You could, instead of like picking one thing and using it as a shortcut, you could pick it and look around it just a little bit, or pick an item and pick up the rest of one.
Right. So pick an item and then look at the items near it. And among those, which one should you pick?
The one that needs to be swapped.
Right. One needs to be swapped. What do you mean? Oh, well, basically like being a little more intelligent, looking at many different potential items, then trying to pick amongst them instead of just using the first one you see. Sure. Other ways we might try and fix things. Yeah.
Since we know that this will perform tightly if the arrays are very sorted, what if we could shuffle the elements we have so that we just some random
Right. So we could shuffle first, and that's actually the way that the Princeton quicksort textbook quicksort works. It shuffles the array first. The idea being there's some distribution of possible runtimes, and the ones that are really bad are extremely unlikely, right? Okay. Any other thoughts? You can make up all kinds of ideas for how you might make things better, but I'll tell you there's basically 4 philosophies to avoid it. So one is smarter, or randomness, which is the approach you just mentioned, where we pick a random pivot or we shuffle. Turns out those two give you the same results. So you just pick any items randomly as a pivot, or you shuffle in advance and always use the leftmost. Same idea. The other one's what you mentioned, the smarter pivot selection, which is trying to pick something better than just the first item. The usual way of thinking is you want to like approximate the median somehow. Why is the median a good pivot? Yeah. Right, you exactly cut the problem in half. The median lands in the middle. You want to get a little wacky, you could do introspection, which is, well, if you find that your code is going too many levels deep in recursion, then you switch sorts. So you're doing quicksort, and then you find out, oh, well, I seem to have gone like 40 levels deep, and it should only be 20 on a random set of data. So this is some kind of pathological data set. So I'm just going to change my mind and not quicksort at all. I'll switch to heap sort or merge sort, something like that. Another is to pre-process the away somehow, which is sometimes, nobody mentioned it this time, but often I feel like students 61B will say, well, check if the array is already sorted, or if it's one of these bad situations. But the problem is you can't really do that. It's tempting as a student. You might have thought about it, even if you didn't feel comfortable raising your hand. And the reason is some bad inputs are not obviously bad. But these first 3 approaches are actually things that people do. Okay. So randomness among those philosophies is my preferred approach. And that's the way that in my opinion, the best quicksort should be done. That's just my gut feeling. Okay. So the idea here is that if the pivot always lands somewhere good, quicksort's n log n, And there are bad situations like the one we mentioned, things are already in order. And so if we want to do randomness, there's two, as I noted, basically identical ideas. One is to pick the pivot randomly each time. So don't use always the leftmost item, or the other is one you suggested, which is shuffle before you sort. And this second strategy, I should note, you need to be pretty careful whenever you write your partition code so that you don't get n squared behavior on an array of all duplicates. Now, this may seem totally out of nowhere, and I'm just mentioning this as a piece of lore on the off chance it ever comes up, maybe at a job interview. The textbook that this class used maybe 7 or 8 years ago, an older version of the textbook actually had a bug in their quicksort so that if it was all equal items, it picked a random pivot. But if you had just the array like 7, 7, 7, 7, 7, 7, 7, 7, it would run in n squared time. So just be aware that if you try to be very clever and shuffle before you sort, that can run you into trouble. Okay. For reasons that are not totally obvious. Anyway, if you're curious, this is a study guide problem box. All right. Now, here's this character I brought here. This is a guy from a TV show I've never seen called Renegade. But at some point, I don't remember how I even Googled this back in the day. But I use this as like my avatar of the quicksort algorithm, right? So Renegade, again, has anybody seen Renegade, the TV show? No, right? It's from the 80s. I certainly haven't seen it even. But it's about a guy who was accused of a murder he didn't commit. So he travels on a motorcycle to solve crimes and fix things up, and has luxurious flowing hair. And the reason I think of quicksort as the spirit, this is the spirit animal guy of quicksort, is that among all the sorts in the universe, turns out that, in my opinion at least, this randomized version of quicksort is the best sort in terms of getting you really good performance. And there's something beautiful to me about that it's not something bureaucratic and boring like merge sort, but it's the devil may care attitude of this this motorcycle guy who hopefully whenever you're trying to remember what quicksort is, you'll just think of him. All right, anyway. So randomness is something that works out in your favor. If you use a random quicksort, you will end up on the tail end of that. You'll never end up in the tail end of that distribution. You'll be in good shape. And you can actually show, this is a little beyond the scope of the class, but let's say you try to be clever and you say, well, I'm going to do what another student suggested. I'm going to pick like 5 items and pick amongst them as the best pivot. But it turns out that if you have a pivot selection strategy that is deterministic and constant time, then it is possible to generate an input that will break the quicksort. So I should note that Java's quicksort is deterministic and its pivot selection strategy is constant time. It grabs something like, I don't remember if it's 5 items or 9 items, but among those, it picks the median and it uses that as the pivot. But there's a paper, which is very clever. If you read this paper, if you've never read a research paper, I think this is a pretty readable one. I think it's from the maybe mid-90s or so. I can't remember anymore. But he describes a way to write code that given any deterministic constant time quicksort algorithm, it will find an input that causes it to go n squared. And in fact, if you run, I wrote a program that implements this paper once, and you can generate an input that if you use arrays.sort in Java, it will get stuck in an n squared situation. It'll actually crash your code. So if you have a web server out there on the internet that takes user input, feeds it to a Java backend, like something you did for Project 2B, and it calls arrays.sort, there's actually an input that will cause that sort to crash because it's a bad input to their quicksort because they didn't want randomness. They didn't want this guy running the shell. Instead, they tried to have something that was deterministic and constant time. Now, is this a serious security vulnerability? I mean, maybe, maybe not. But it's interesting that it lurks in any quicksort, which is deterministic and constant time. You run into some trouble. Now, if we had time, I mean, I could do another entire lecture on why this happens exactly, because quicksort, again, is my favorite topic in the class. Maybe I went a little too wild here, telling you things you might not need to know, but just be aware. Kind of a fun topic. If you want to know in office hours, happy to talk about it sometime. All right. Let's talk about strategy 2B, which was the picking a smarter pivot. Okay, that's in contrast to 2A. So 2A was that idea, let's just pick a few items and pick the best one among them and use it as a pivot. You run into this trouble. 2B, where you actually pick the exact median, that one's okay. That one's going to work fine. We'll call that exact median quicksort. The steps are, first, find the median of the items, then use that as the pivot, and it is guaranteed, as you noted, will always land exactly in the middle. Okay. Now this one will have worst case n log n, because again, the algorithm is, I got a quick sort. There's some potential danger, right? Like, yeah, technically I could run into this n squared situation, but philosophy 2b is very safe. It actually looks for the median, uses that. And if you always use the median, you're never going to end up in a bad circumstance, okay? Now, the problem with this approach, it turns out, is that the cost to find the exact median ends up it's expensive, and it results in an overall sort that is slower than merge sort. So if you give up the randomness, you no longer get the timing advantage versus merge sort. I mentioned last time quick sort's faster than merge sort. Once you do this, it's not faster anymore. It's just like an empirically observed fact. I can't explain it to you in words. It's just something that if you run the experiment with real code, you will find that to be the case. It does raise an interesting question, which is how do you compute the median of an array? And we'll get to that later today. Okay. All right, any questions about this? I'm kind of like philosophizing. So there's a lot to digest. This is like 25 minutes of lecture in 7 minutes because I'm giving a high level picture. Any questions about these things? So just like to back up slightly, I said there's 4 philosophies. There's randomness, which is my preferred. You run into an extremely rare circumstance, basically vanishingly impossible, that you get n squared behavior. Then you have smart pivot selection, which can either be constant time pivot or linear time pivot. Constant time pivot is what Java does, but it's open to this attack that was published in a paper. Then there's the linear time version, which is not vulnerable, but then it's slow. It's a lot of interesting tensions here, to me. All right. Introspection. So we could also just watch the recursion depth if I noted. So if we get beyond, say, 10 natural log n, that's a lot more than the expected 2 natural log n depth of the recursion tree. And you can do that. That's not super common in practice. I don't really know why. Okay. All right. So wrapping up our sorts so far, we got selection sort, insertion sort, merge sort, and partition sort. And really, maybe the bigger picture thing, instead of kind of the nitpicky details that I find fun, but I didn't really give you a full amount of time to digest, is the fact that all of them are based on a different basic operation. Selection based on selecting, insertion based on inserting an item, merge sort is based on merging 2 sorted arrays, and partitioning is based on partitioning around a pivot. And again, was created by an amateur, and kind of interesting that ends up being the most mathematically rich and fastest sort around. Okay. In terms of which one should you use? Well, turns out that merge sort and quick sort on big arrays, they're going to be faster than these other approaches. Heap sort, while it is technically n log n, it has bad caching performance, and 61C will explain what that means. Insertion, when should you use it? If your array is tiny or almost sorted. Merge sort and quick sort. Right now, we have no reason to not use quick sort or merge sort, but we'll have a reason by the end of the lecture. Okay. The quick sort overall, if you give me a random piece of data, quick sort's going to generally do better than anything else. Okay. And again, one of the things I love about quick sort is it has this Achilles heel that it can go n squared, and there's a lot of clever ways to try and get around it. And none of them is like Pareto dominant over the others. They all have their own flaws. Okay. Now, I said quick sort's the fastest, but I'm gonna tell you just a little bit more about practical quick sort implementations. That's only true if we make the right decisions. We have to decide how to pick a pivot. Question for you, how do we pick our pivots? In my demo. Get an array, how'd you pick the pivot? Leftmost, right? We could do something else. The partitioning algorithm. How do we do partitioning? It was the algorithm you guys came up with, where we fill in all the red items, then the white items, then the blue items. And then how do we deal with avoiding this worst case? And it's possible that your 2 choices above here make it so that the worst case never happens. So what I'm not going to do is the live comparison, because I was trying to set up the demo and it was just quirky in a funny way. I don't need to explain. But if we speed test merge sort versus quick sort, if we use the procedure where we always use the leftmost pivot, and then the partitioning algorithm is make a copy where we fill in the red, then the white, then the blue items, and then we shuffle before starting to avoid the worst case, turns out that the runtime difference between merge sort and quick sort was 2.1 seconds versus 4.4 seconds. Now, this is only one possible quick sort. This is the quick sort that always uses leftmost. that scans through the array and my implementation 3 times. So find all the reds, find all the equal items, find all the blues, all the greater than or equal, or all the greater than items. And then the way we avoid the worst case of shuffling ends up being slow. Okay. All right. So I want to do better. So what Tony Hoare did, and this is even weirder to me that he was just some guy coming up with quicksort, is he didn't do the approach, which is just copy all the smaller things, the equal things, and the bigger things. What Tony did is he had, I'll show it in a demo, but he had 2 pointers that walk towards each other. And anytime they run into trouble, something they don't like, they swap. So let me just show you a demo because that'll just make way more sense. All right, so here's the idea behind Tony Hoare's partitioning scheme, the one in his original framing, is that here's your pivot on the leftmost side. So we're assuming that it's not the leftmost side. And they're gonna have 2 pointers, L and G. And you can think of L as a friend to small items. And here when I say small, I mean small relative to the pivot. So who's the boss? 17. So L is gonna look at each item with an eye towards the boss and decide, are you smaller? G is gonna do the basic same thing. And it's gonna be, you can think of it as a friend to large items. And both of them don't like equal items. They're basically gonna walk towards each other until they both see something they don't like. And then they're gonna swap. So let's see an example. So question for you, here's L. L likes small items and does not like large or equal items compared to the pivot. So does L like 15? Yeah, it's great. You're a good buddy. Hi, lovely 15. I'm gonna move on. Okay, so now we get to 19. 19 though, this is not great. Like this is bigger than my boss and my job is to find things that are greater than or equal to the boss. We found, okay. How about G? So this is G's first moment on the job, right? So she's been through training and she immediately runs into a 17. What does she think of 17? Does she like it or don't like it? Don't like it, right? I dislike 17. Okay, good job. So it's like, you know, flight attendant, first day on the job, you got to go down the slide. Good job. You know, you figured it out, even under pressure. Okay. Now what they're going to do is they're going to trade. And the basic idea is that the invariant under the hood here is that L has landed on an item which is disliked and G has landed an item that is disliked. So they're going to swap. Okay. So we're going to swap these 2 items. They're going to toss them in the air. You could think 19 and 17 are going to swap and there they go. Okay. And when you swap, you'll step forwards. Now, the basic idea is that's going to ensure, so whatever G was stopped on was something that was less than or equal to. So that gets passed over here. And wherever L stopped is something greater than or equal to. Now, you might say, this seems a little more complicated. Like, why are we bothering to swap the 17s? That goes back to that classic problem I mentioned in the old algorithm textbook. If you don't stop on the equal items, you can run into n squared behavior. So that extra layer of not liking the equal items that seems totally extraneous is to avoid n squared behavior on all equal items. It's something you got to think about later, not right now. Okay. So they have finished their swap. And so now L looks at 32. Does L like 32? No, you are not good, right? That's not good. This is immediate trouble. Great. How about G? What does she think of 17? Hate it. Exactly. Same problem. Trouble here too. So now what's going to happen is they're going to swap. And when they swap, they step forward. It's a complicated sort of ballet-like maneuver where they toss the items in the air and they step forward. But I don't have an animation for that. You have to use your imagination or come to class just super high. One of those two. Okay. Boom. There we go. All right. So L is looking at 2. Okay. All right. Is 2 okay? Yeah, seems great. We're going to 2's cool. Okay. 26 is disgustingly above the number that I want it to be. G, what does G think of 41? Fine. G gets there. 26 is fine. Now they've crossed. It's like 2's no good. Oh, also hi L, we cross. So do we swap these? What do you think? Just knowing what we're trying to do. Why? Right. So we swap these. That's not the right thing to do. We're doing this to partition, right? So if we move the 26 here, then 2 over here, we've just made ourselves trouble. We're trying to get the bigger, all the items over here to be bigger or equal, and all the items here to be less than or equal to. Okay, so now we're basically done. We're done walking. And at this point, is this array partitioned on 17? Not quite. What's the problem? There's a 2 here. So what do I need to do? And I'll give you a constraint. I mean, the answer's on the slide, but try not to look at it. So we have G and L right here, and we have a 17. 17 should land somewhere, related to G or L. Like where does it go? What does it seem like the right place to go? So if you wanted to swap 17 so that the partitioning process is done, where should it land? Yeah, G, right. So we're gonna swap there. Okay, so this is, I've landed here, and then the new pivots for the next subproblems will be 2 and 26. So that's the last step, okay? So this algorithm is not obvious. It's seemingly very arbitrary, especially when you first learn it. But after you've done it a few times, and even better, if you try and explain it to someone else, it becomes very natural. But I don't want you to have it memorized just as a set of pointless steps. If you get to this point, say around the midterm or the final, and you're trying to remember, do I swap a G or L? I accidentally typed my cheat sheet and the GSI took it from me. What should I do, right? Well, I just have to think about it and say, okay, well, if I swap with L, then it's not gonna be right. So it's gotta be G. And it turns out to be right in this case. All right, there you go. So that's Tony Hoare's partitioning strategy. It's different than the one we did, but it's turns out to actually be faster in general. Okay. Any questions about this process? Okay, so it's mostly about the characters. I encourage you to run through this demo again. Think of L and G as doing their jobs, and they're done. Okay. All right. Okay. So it turns out that if we do this strategy, which I should note, there's something very different about this approach than the old one, which is that it is in place. You don't have to create a separate array and copy stuff over. And it's for that reason that you end up doing a little better than the other approach, or a lot better. By the way, merge sort, one of the reasons that merge sort is slower is, again, because it has to do all this copying. You're always taking two arrays and then copying it over to one bigger array. And the overall overhead for that ends up being expensive. Okay. So this approach, if I run the timing test, we end up getting a 1.7 seconds on the demo I did on my desktop computer, which you'll notice is faster than merge sort. Okay. Actually, I'm gonna go back one slide real quick to say that this partitioning scheme is now a very fast quicksort. There's actually faster versions than this, and I'll talk just very briefly about one of them in a bit. But the overall runtime is still going to depend on the pivot selection. So this partitioning scheme is better, but this pivoting selection strategy, it still affects them. Okay. All right. Now there are more recent schemes. So this one I gave it a different name. This is not a standard name, LTHS. L is the pivot. So they're both L, they use the leftmost. They both involve shuffling, that's the S. But the partitioning algorithm is different. I did the scanning through the array 3 times and making copies. This is the Tony Hoare stuff. Right. Any questions about this? So there's more recent strategies. You can make up your own stuff. And maybe you think it's fun. The version of Quicksort that was the best known in 2019. I have not actually double checked since then. But it was a 2-pivot strategy that, interestingly, was just posted on a random Java forum. Now, Quicksort is not a Java thing, but there was someone who was like, hey, this is very small. Hello all, I'd like to share with you a new dual pivot Quicksort, which is faster than the current Quicksort. I think we should change Quicksort to this one, and explains what goes on. And it was just some random guy nobody ever heard of, Vladimir, I forget his last name. And ended up actually replacing the Quicksort in Java and then also other languages because it turns out to be pretty good. So it's just some random post, basically. Some guy nobody ever heard of came up with a new strategy involving 2 pivots. I believe this actually has been revised and in different environments. I've even heard of a 3-pivot Quicksort, but I don't really know how they work. Okay, but kind of fun. So for those of you who ever think at office hours, well, what happens if I do a heat, but I do this one quirky thing? Maybe you invent something new. And I should note that the guy, John Bentley, that was in that thread right here. So he's a very famous author in the world of programming. And he wrote this book called Programming Pearls. It's very, very good. And he, I believe, I don't remember if he wrote the Quicksort that's in Java originally or not. That might have been Josh Bloch. But anyway. So I don't know Josh Bloch, but I always like this name with that sound. But yeah, so he basically said, Tony Hoare developed Quicksort. I was proud to make contributions to a nice Quicksort in the 80s and worked on it over time to make it better and better. but I think that Vladimir's contributions to Quicksort go way beyond anything I've done, which is pretty cool. That just some random post, some guy invented a new Quicksort and suggested it for Java and ended up being better overall. Yeah. One of the things that's really interesting to me about these Quicksort type algorithms is that you can't really prove in advance that they're better. You just have to like come up with the idea and run some experiments. And I think that's pleasing. All right. Now, what if you don't want randomness? I guess first question, why would you not want randomness in your sort? If it works, why don't we just use it? Why does Java not have randomness in their sort? What do you think? Yeah. There's no real randomness, right? The randomness has to come from somewhere. So when you ask for a random number, do you guys know where they come from? Like in Java, use like a random integer generator. Do you guys know by any chance? Yeah, so there's a type of algorithm that there's this random seed. You pick a number and you can think of it as the first random number. And then it takes that number and does some computation to deterministically figure out what the next random number is. And it looks random to you, but there's actually a deterministic sequence that you're iterating over where you're like jumping over the space of all integers, but in a deterministic order is the grim truth. You can layer things onto that to make it a little less deterministic looking, but randomness in general on a computer, it's mostly actually deterministic. There are ways to collect random information. What's an example? Like if you wanted to get some randomness, and some of you in like the crypto space may have had to generate real randomness before. Right. You can just see whatever happens to be on the camera. That's a good example. Other examples of true randomness. Yeah. Yeah. There's the lava lamp thing. Yeah, Cloudflare, I think, is the company that has the wall of lava lamps. Yeah, it's a good one. So random, like a physical process you're observing. Yeah. You can do some radioactive decay. That's really random. Yeah, hard to predict that one. Theoretically impossible, in fact. Pretty deep, that one. You got the, go ahead. Right, yeah, just have the user like wiggle their trackpad around. Exactly. So that's more or less random. I mean, it's random. It's your brain, who knows? Yeah, but it's.
I think if you measure it, like 90% of people are going to wiggle their finger on the trackpad in roughly the same way.
Yeah, so there's like, maybe there's bias in the way people wiggle their trackpad, perhaps so, yeah. And so people don't like, randomness has to come from somewhere. So it means if you wanted to make Quicksort in Java random, that randomness needs to come from somewhere. It could either be a black box randomness that's hidden from the user, but then that means that your code's gonna be really hard to like replicate what's going on. So you want your code to hopefully be predictable in some way. Like if you're trying to debug your project 2B and you were using sort, it'd be annoying if every time you ran the debugger, you got different output because the sort was a little bit different in terms of the way it was random. And we'll come back to why that might occur. But if there was some really subtle bug in like your sorting routine, having randomness is a pain to debug. The other reason is that you could actually expose the randomness as part of the API, so that arrays.sort in Java, there's a parameter which is a randomness source, but that's awkward. So what the Java designer said is we don't want black box randomness, and we also don't want to pollute the API with requesting randomness, so we're just not going to have randomness at all, and they accepted the danger of possibly going n squared, okay? So if we don't want randomness, but we want usually pretty good behavior, what Java did is that they used an approximation of the median. I guess I kind of want to come back to understanding just at a little bit deeper of a level of why not just find the darn median itself? If the median's so good, let's just get it. So the best possible pivot is the median. And so I'm just going to pose the question to you. How would you find the median of an array of numbers? Okay, so come up with an algorithm for finding the median of an array, and extra bonus points if your algorithm is only linear time. But good luck with that. All right, I'm gonna give you guys like 30 seconds. Imagine you got to find the median of a list of numbers super fast using some algorithm you devise.
Do we get the list on?
You get the length of the list, sure. Okay. What do you think? Someone give me an algorithm. Finding the median. It could be kind of silly. Just has to work. We have an idea? So coming up with a clever algorithm is very hard. Coming up with kind of a obvious algorithm, maybe less so. What do you think? Yeah. Love it. Perfect. Great answer. Okay. I was going to take that as okay. Sort the array. Return the middle item. Okay. Why is this a bad strategy to find the median for quicksort? You don't want sorting to be a subroutine for sorting. Exactly. Okay, good. So this actually raised an interesting question. Could I do median somehow better? Yeah, it turns out there's an algorithm called PIC. Well, it's actually now called BFPRT for Blum, Floyd, Pratt, Rivas, Tarjan. This is an amazing paper to me that this ever happened, but there's an open question in computer science for a little while, not for too long, about could you find the median in linear time? Turns out yes. And this list of names is totally ridiculous because 4 of these people have Turing Awards, which if you don't know is like kind of the Nobel Prize of computer science. And then there's also Von Pratt, who's the one person on this paper not to get a Turing Award. So kind of amazing to imagine. Bob Tarjan, by the way, was when I taught this class at Princeton, there's a funny thing where they have faculty cycle through as one of the TAs for a class every so many years. And Bob Tarjan was my TA once for this class, which was fun. So he has a Turing Award in graph theory. And there was one time we were doing an exam problem and he couldn't figure something out and I got it. And I felt like the smartest person in the world, but I was kind of cheating because I thought about this kind of class problem a lot more. But there was one time I was slightly faster than Bob Tarjan. So, but he is a vastly amazing human being in so many ways. Anyway, okay. So let's say we take the BFPRT algorithm, which is a linear time median selector, and we use it as our selector. If we actually ran this code, I should add the code to lecture code repo, actually. I have it all. But if you ran it, it's actually extremely slow, 10 seconds, right? So it's safe, but actually way worse than just using merge sort, vastly worse. The cost to compute the median is too high, even using 4 people with Turing Awards, clever idea from the 70s, okay? So if we want good practical performance, we have to live with this n squared possibility, whether or not that's like a super unlikely shuffle-based n squared or opening yourself to malicious input style like the Java folks. Okay. All right. Okay. Any questions? That's the end of the quick sort. I hope you enjoyed the tour. I know that this is a bit of a Swiss cheese picture of quick sort, right? I like kind of danced around all the little holes and we didn't really get the full details, but I hope you gave you a sense of why this is such a rich field. Maybe someday I'll actually do 3 quick sort lectures instead, so we get all of it. Then I got to give you more problems to do in the middle so I don't get bored. Go.
Why do we find the exact median? Like, can we?
So you can approximate the median. And so, yeah, if you do an approximate median, that's a good question. Is there a middle ground where you do like find, so if you look at a constant number, if you do a constant time median selection strategy, in that case, you definitely have an n squared input. It's guaranteed by the McIlroy paper. If you did some approximate median that wasn't the true median, but it was still linear time, there might be some daylight where you could squeeze something out, where it's maybe not the median, but it's guaranteed to be like kind of median-ish. So maybe it's 1/5 the runtime of PIC. Maybe you could find something better, and maybe that'll be an improvement. In the same way that Vladimir, gosh, I really wish I had his last name because he did this important contribution as a no-name person, which is super awesome. Maybe there's something like that, like a pivot selection strategy that ends up being super good that no one's found yet. That's an approximate. All right. Let's have a quick select. This is Quicksort's cousin. So this is the selection problem, which is computing the exact median is great for getting an item to partition around. It gives us some kind of safe quicksort, but it turns out that exact median computation is too slow. Now, actually, interestingly, let's say you do really care about the median for some reason. Like you have some application where someone gives me some data and I need to find the median as fast as possible. I don't know why that would come up, but if that happened, how would you do it? Should you use the PIC algorithm or should you do something else? Turns out that you use something very closely related to quicksort to find the median. If the goal is just to find the median, I think this is pretty fun. So this algorithm is the best known median identification algorithm, and it is Quicksort's cousin, okay? All right, So I have a woe here because partitioning, the danger of partitioning is that you need the median for partitioning to be good for quicksort. But it also turns out the partitioning is the best known algorithm to find the median, hence the Keanu Reeves face. This is my last of 2 Keanu Reeves faces that I have, and they're both quicksort related for good reason. All right. So the idea here is, let's say we have this array. We want to find its median. Okay, here's 9. This is the first pivot I'm going to use. I'm going to partition the array. I'm not sorting. I'm trying to find the median by using the leftmost item. So we partition the array and it ends up here. That's just the same procedure from before. 6 and 5 are the smaller items. 550, 14, 10, 330, 817, 913 are the bigger items. Okay. So 9's not the median. How do I know? I mean, you know, because you're a human, you can just look at the numbers and tell it's not the median. How do we know, based on this operation, that it's not the median? It's not in the middle. If it were in the middle, it would be the median. It's not in the middle. It's actually the 0, 1 tooth item. I know that that's its rank. I don't know about anybody else. Okay, so what do we do next? Could the median be over here? No. Could the median be over here? Yeah, so we're going to partition on 550. Okay, 550 ends up there. Is it the median? No, it's not in the middle. Where could the median live? Here, left or right, or both? Has to be on the left. So it's like quicksort, but we're throwing away the other subproblem, right? Notice we never actually looked at the 6 and the 5 again because we know they're not the median. Okay, good. Okay, repeat that process. We end up getting 14 as the median, and we know that's good because 9 over 2 is 4. Okay, that's the best known median selection algorithm. So you partition the array on an arbitrary item. If it lands in the middle, you're done. If not, you only look at half of the array. What's the worst case performance for quick select? So we do this process. Any idea? Yeah. It's actually worse than in the worst case performance. I'll show this picture again. So this is a reasonably good case. We moved 9 here. We got to delete all these items, got to delete all these items. What would be the worst case if this was what? If it was 5, it was the smallest item, then you would just have to partition again. So what would be the worst case? Kind of just smelling that out. N squared, yeah. So the worst case that could possibly happen is we have the numbers 1 through n. We partition on 1 and nothing happens. 2's the next pivot, then 3's the next pivot, and so forth until we get to n over 2. So if you're in sorted order, you're not doing any shuffling, it's going to be n squared time. Okay. Now, on average, quick select takes theta n time. This is maybe what you're getting at. This is the harder argument. And this is the intuitive picture again. So let's say we pick an arbitrary item and it ends up here. That's just a random place. And we're going to throw away the left items because we know the median's not there. Here's our new pivot. Let's say it ends there. Which side of the array do we keep? Could the median be on the right? Could it be on the left? Good. Not on the right. Yes, on the left. So we pick a new pivot. Okay, ends up here. Okay, throw away that side. That's the new pivot. Ah, okay. We got lucky, I think. That's the middle. Doesn't look like the middle, but it's an illusion. So the idea is that on average, the pivot is going to end up about halfway over, roughly. Not exactly halfway, otherwise we'd be done, but just on average, it's around n. The time to do that first partition takes n time. That's what this refers to. So finishing this partition operation took n time. And then the second time we did n over 2 work to do the second one. And then n over 4 and so forth. So it's like you're cutting a problem in half over and over and throwing away the other half on average. Okay, this is just a very crude measure, but n plus n over 2 plus n over 4 plus n over 8 and so forth is just theta n. All right, kind of a recall of the same runtime we saw before. And so that's pretty fun, I think. All right. Now, this is quick selected. So if you need the median as fast as possible, this is how you do it. So it's kind of interesting to think like, it's very weird to do this, but what if we use quick select to find the exact median? So the resulting algorithm, I didn't actually write the code for it, but it's still quite slow. And I have to also note, it is very weird to do a bunch of partitions to find the best item to partition around. You can do it. I wrote the code. I never bothered running the experiment, but it's not so good. Okay, but yeah, Just kind of throwing that there as a fun thing. But just so you know, I think that's another thing that makes this specific area of intellectual inquiry really interesting, partitioning. So what does partitioning do for us? It gives us the fastest known sort. It gives us the fastest known median finding operation. And then there's this weird sort of anti-duality almost is the way I would phrase it, where you need the median to get the best possible quicksort. But then the idea of partitioning is also the best known way to get the median at this point in time, at least. Okay, moving on. All right, that's the end of quicksort for you. And so I hope you found that fun, maybe a little intimidating because it seems like there's a whole universe of weird stuff going on here, but I think it's great. Okay, I'm gonna wrap up our discussion of the core ideas of sorting by talking about one last property of sorting, which would be really important to understand why Java does sorting the way it does, something called stability. Okay, so just as a reminder, we got selection sort, insertion sort, merge sort, and partitioning sort, also called quicksort. And here's all their runtimes. And so the question is, which one do we use? Okay. So it turns out that Java uses both merge sort and quicksort in two different circumstances. And it's going to be all based on this idea of something called stability. So we'll say that a sort is stable if items that are considered equal under the ordering, that is neither A is less than B, nor is B less than A, for all such items, if their order is preserved after the sort. So for example, here's a bunch of random people whose names are randomly generated by a website, thank you website, and we're sorting them by name, okay? If we sort them by name, here we go, and what we end up with is the following. Wait, let's see. This is after we sort them by name. So notice that they're in alphabetical order. Boss, Jana, Joni, so forth. Okay, that's all of them. If we now sort by section, what you'll notice is that how many people over here were in section number 3? 4 of them, and they're in the same relative order. Okay, so this is a stable sort because afterwards, the students within section 3 are still in the same alphabetical order. So they don't cross over when you do a stable sort. Google Sheets, for example, and Excel, their sort function is stable. And that's useful because often when I'm doing data analysis of things for this class or real life, I like to have them sorted by both section and name. So if you want to have every section sorted alphabetically, this is a strategy. Sort by name, then by section. Okay. All right. By contrast, if your sort was unstable, that property would not be guaranteed. You might end up with, in fact, often you'd end up with not in order anymore. And this could be annoying. Let's say I want to I'm going to sort the class by section and then by name so I can like find somebody or like, I don't know, whatever it might be. Or maybe I sort the class by section and then by grade or something. I don't know what. Never mind. I'm going to stop coming up with scenarios that are dumb. You get the idea. Okay, cool. So question for you, just to see if you can feel it out. So I'd like you to think about my question might only have one of these two. So is insertion sort stable? And is quicksort stable? So I just want you to think about those two problems for a second. So I think I messed up on the Yell key and it only has one of them. Give it a shot. Oh, they're both there. Yes. This is the first and only 2 question, Yell key. All right. So insertion sort turns out to be, yes, it's stable. The reason is, let's imagine we have an item which is equal to another. So we have such an example here at E. Now E, whenever it swaps backwards, boop, 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 it does not go past its buddy E. So when the process of insertion sort is proceeding, we don't cross over equal items. For that reason, it is sorting, or it is stable. Quick sort, kind of a trick question. So I think those of you who said no, I feel a little better about it because I've been talking so much about randomness. But technically speaking, you could do a stable quick sort. So the quick sort, which uses the 3-array copy thing, where we put all the red items and the white items and the blue items, and which we don't shuffle, that one's stable. But most quick sorts, in fact, basically any practical quick sort is going to be unstable because of the fact that it uses shuffling to avoid running into n-squared behavior. And if it doesn't use shuffling, it's still going to use this Hoare style partitioning where items get crossed, where like L finds 17 and G finds 17, and they're like, let's trade. So for that reason, quick sort's just going to end up being unstable for the most part. Okay. All right. So we can add an extra column to our sorts and say heap sort is not stable, insertion sort is stable, merge sort, I didn't tell you this, but it's true. You can think about it later. And then quick sort is not stable. Heap sort actually is another one you'd have to think about. Turns out also not to be stable. And you can think about these two as separate exercises. Okay. This red text is just the thing I said out loud. All right. Let's talk a tiny bit about optimizing sorts. This is Tim. He's on the slide. I'll tell you who he is in a sec. So there's extra things we can do to improve our sorts beyond trying to make them stable. Like that might be a desirable goal. If you want to make sorts even faster, when you're trying to think about which sort to use, we can switch to insertion sort whenever the subproblem size gets less than 15 or 30 or 40, depending on what kind of computer and data you're using. And why do we switch to insertion sort for small amounts of data? You guys remember? It's just fast. It's just empirically fast. Another is to make your sort adaptive, which is to exploit existing order in the array. So for example, in Python, that's the sort. Like when you do sort in Java and Python, it uses something called tem sort. This is tem, and it's just an optimized version of merge sort where it's got a bunch of little tricks at place. I'm not going to try and explain them because I've dumped a lot of random factoids on you. But if you're curious, you can ask me later. And it's also one of the main sorts in Java, does something very similar to tem sort. There's also other funny things you can do, which is if you know things about your data in advance, like there's only 4 different keys that occur, then there's tricks you can play to get linear time sorting instead of n log n. Here is a link if you're curious about such an algorithm. And as I noted again, with quicksort, you can do an introspection. If you're running quicksort and you find that it's taking forever, you just switch to a different sorting method if it's going too slowly. That's only a problem for deterministic flavors of quicksort. And just beware, these are just different tricks you can play if you wanted to go even more industrial strict. So the last thing I want you to think about today is the following question. Arrays.sort in Java uses merge sort, specifically tem sort, merge sort. It's not quite the same as the Python one, but very close. If some array, the thing you're passing in, is an array of objects, and quicksort if it's primitives. Why is that? Something to think about. Maybe you can sniff it out. Something related to something we've been talking about. So I got it as an eye-level question. So what I encourage you to do is like argue with somebody else about this question in class at some point. It's pretty interesting. Okay. I'm actually going to save this fun bit for our wrap up of sorting totally next week. Because then you'll have seen one more sort that's different. Okay. So we're done for today. Hope you had fun. I will see you guys on Wednesday. Okay. Yes, I got it. I think I have office hours now, so you can walk with me. Let me see. Yes. Yeah, how's that? I have to remind everybody. I have office hours now. If anybody wants to go to it, see you there. All right. Let me turn this off. Bye, internet.